This is the Daily Space for today, Thursday, June 18th, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Now, when labeling astronomers, we generally fall into a very small number of categories. There are the observational folks, the computational folks, the theorists, and the instrument builders. That's most of us. And many of us will wear more than one of those labels during our careers. Now, our combined efforts build the instruments that are used to observe our skies and test our theories against reality. And when those data sets get big enough and those theories get complex enough, we throw computational might into the problem. But sometimes our computers just can't handle the complexities of the universe in the needed detail. The interactions of myriad particles in the planetary atmospheres and the propagation of shock waves in supernovae are all problems that we can approximate in computers, but our approximations just don't look like the reality we observe. Simulations like these are when we turn to one of the rarest kinds of astronomers, the laboratory astrophysicist. These folks build equipment that simulates the specific conditions of different astronomical events and recreates our universe in a box, or in the case of today's top story, in a pizza-shaped wedge. Now, the Hubble Space Telescope and other high-resolution systems have allowed us to see supernovae remnants as complex, lumpy, bumpy systems that are each unique. There's a myriad of them shown here in this image. Those colors, those colored images, those are real supernovae remnants. Trying to recreate the complex leading edge of these systems has proven more than our computer models can handle. Now, though, there's a laboratory option. Researchers at Georgia Tech have created a supernova simulator in their lab. Like computational simulators, it only looks at a section of the explosion, a wedge expanding away from the, simulated core. But this system provides enough three-dimensional particle interactions to recreate supernova physics in a way that has previously just not been possible. In an actual supernova, the core of a star will collapse after it runs out of fuel to power the light-producing nuclear reactions that normally support the star. This collapse triggers a powerful explosion that pushes the high-density star material in the inner regions of the star outwards, where it mixes violently with the surrounding lower simulator. This system is recreated as an actual explosion that pushes up through two different layers of high-density and low-density gas. That's what we're seeing in this video. According to the press release, heavier gas in inner layers stabs turbulent outcrops into lighter gas in the outer layers. Then behind the blast wave, pressure drops, stretching the gases back out for a different kind of turbulent mixing. The final structures of the supernovae are shaped in part by the naturally forming irregularities at the boundaries between the two densities of gas, irregularities that are there even before the shock wave. These perturbations are stretched and skewed at angles when blasted by the explosion. Now, the supernova in a wedge machine, it's allowed researchers to take high-speed images of what's going on at the density boundary and capture the formation of these iconic supernova structures. Along with the regular bumps and bubbles, they also observe turbulent spikes of high-density gas pushing into the low-density region and bubbles of light gas trapped in the areas of high-density gas. In addition to defining how these shock waves drive through the system and how structures form, this physical simulator also allows researchers to better understand the timescales of these structures' evolution. This will ultimately help us better date the formation of observed supernova remnants. And apologies for the dog barking in the background. This is our plague time reality. Anyways, this is cool research, barking dog or not, that makes it clear that sometimes you need to try and recreate what you see in the sky. And it is only in that recreation that you can understand what you see. Laboratory science doesn't always go in that direction, however, that direction of see something, then recreate it in the lab. Sometimes we see things in the lab we need to go searching for in the universe. In our ongoing search for the origins of the stuff of life, scientists have worked to understand what molecules life needs and to then see where they can be formed. One of the more fundamental molecules in life as we know it is the amino acids. These molecules are primarily composed of carbon, nitrogen, oxygen, and hydrogen. And the human body uses 20 different amino acids in its various functions. Amino acids have been observed in interstellar molecular clouds since 2003. And in a new paper accepted in astronomy and astrophysics, researchers have gone looking in the lab for the precursor molecules to amino acids. And having found those molecules, they've turned around and looked in astronomical data for them. And they have found these precursor molecules in space. The molecule in question is proparglamine, and it has been found in the molecular cloud G plus 0.693 minus 027, which is located in the direction of the galactic center. The chemistry behind these molecules can take place in cold and icy areas, including on the surface of icy dust grains and even on the surface of asteroids or within comets. While we here on Earth benefit from warmer production methods of these molecules, it's intriguing to see that the building blocks of life could have been brought here rather than made here. Now, for our final story of the day, I'd like to call your attention to some particle science results that we're going to be following. Scattered around our world are a variety of underground detectors that are protected from the random noise of space and are tuned in to look for the specific flashes of light that can occur when particles like neutrinos collide with specific liquids. One particular detector, the XENON1T in Italy, is filled with ultra-pure liquid xenon. Designed to search for certain theoretical kinds of dark matter, it has so far found none of the particles it hoped to find, but it has found a weird background particle. It's not so much a weird particle it's found, but weird particle interactions that just weren't expected. While there is a chance that all they're seeing is noise created by a few stray tritium atoms, a special heavy form of hydrogen that got into their detector, they could also be observing some kind of a previously unobserved particle like axions from the sun, or they could be seeing an effect caused by neutrinos just having a slightly different magnetic moment than currently expected. Since it would only require a few tritium atoms for every 10 to the 25th number of xenon atoms to cause the effect that's observed, I'm not going to suggest it's time to get excited about potentially new physics. It's still cool, though, to see discussed the possibility that axions are being detected as noise in a dark matter detector. Well, admittedly, dark matter is not being detected. Nevertheless, we're pretty sure this result will turn out to be absolutely not exciting. But just in case it is, we'll be keeping an eye on how this story evolves. For now, though, this is all the science we have for today. I would like to remind everyone that there is a solar eclipse, an annular solar eclipse visible to people in parts of Africa, the Middle East, and Southeast Asia. We will be bringing live coverage of this annular eclipse to you from a couple of our community members, Saturday night going into Sunday morning North America times. It's going to be early morning for them in the Middle East. So stay tuned. More science is always happening. But for now, this has been the Daily Space. I'm your host, Dr. Pamela Gay, and I'm so glad you're here.